Okay, so I'm going to introduce you to MPAS-Analysis, which is one of the diagnostics tools used to look at output from E3SM simulations. And this one specifically focused on the ocean and sea ice components of E3SM. And the main developers are me, Xylar Asay-Davis, and Milena Veneziani. And then there are a bunch of people who've contributed over the years to different subsets of the analysis or different capabilities. So they're all listed here, and we thank them very much. It's always nice to have lots of people involved. So I'm going to talk about just some brief details on setting up and running MPAS-Analysis, but Luke mentioned that there's a tutorial that's going to be coming out later this month, hopefully even next week, and that will include sort of a more detailed walkthrough of how to run MPAS-Analysis and some example results, some example simulation results to use to run the model, to the analysis. Okay. Then I'll talk about some example results, and I'll focus on different types of analysis that might be of interest to the 3 different science campaigns in E3SM. I'll talk about what the most common configuration options are for those of you who might want to run MPAS-Analysis. Basically, what do I have to change to just get up and running with MPAS-Analysis? If there's enough time, I'll go into some of the details of sort of how MPAS-Analysis works under the hood, not in a whole lot of detail, but just a little bit to give you a feel for what makes it, for example, different from E3SM diags or other diagnostics packages you might be familiar with, and what you might need to know to get running on, say, a new mesh, that kind of thing. And then I'll go into just 3 of our future plans for the package. All right, so how to set up and run MPAS-Analysis, just some basics. So mentioning just a third time that there's going to be a tutorial. There's also some pretty thorough documentation about how to configure the model, what the different analysis tasks are, and that kind of thing. But just the really basic gist of it is that you need to install Miniconda 3, which is also what I use to install the E3SM unified Conda environment everywhere. So it's a pretty sort of standard part of our diagnostics workflow. So those are the gist of how you do that. And then you need to download the observations that go with the analysis. Without those observations, the analysis is really not particularly useful. And they're pretty big, so that's not an insignificant download if you want to do it on your home computer or that kind of thing. So just keep that in mind. And then basically then you need to find an E3SM simulation you want to analyze, so give a base directory to it. And somewhere within that base directory, you have to have a run directory where there's a restart file for MPAS Ocean and actually also for MPAS Sea Ice. Then there needs to be some time series of monthly average data for both the ocean and sea ice model. So you can give a path to that. So for example, if you've done short-term archiving, they might be in a different location than the run directory. And there's a way to specify that. And then MPAS components have these concepts of nameless files, which are true for all of the components, but also streams files. And these streams files basically define sort of what the file names are for standard output from MPAS components. And MPAS-Analysis uses those to basically figure out what the names of files are and what variables are in those files. So those are also needed. So this makes it a little bit trickier to, for example, pull data off HPSS because it's not sufficient to just have the time monthly data. You need the monthly data and the streams files and the nameless files and a restart file. Okay, so basically the main task of setting up MPAS-Analysis for a given run is to take a config file, and we have a bunch of examples, and alter the config to do what you want to do. And so these are standard Python config files, sometimes called INI files. They're also used in Windows. And really there are more than 1,000, I think I counted 1,300 configuration options in MPAS-Analysis. So on the one hand, that makes it really flexible, but on the other hand, it makes it really overwhelming. So that's part of the reason that we have a bunch of examples with just the sort of most common configuration options that you might want to change. And we also try to document even the default config file pretty thoroughly, just so that it's clear what each option might be useful for. So if you're wanting to get started with MPAS-Analysis, come talk to us about how to do different configurations that might be a bit different from the default if you need some help. So that's configuration. I'll get into it a little bit more later in the presentation. But then basically, once you've got the config file going, you are ready to run. So you just do MPAS-Analysis and give it your config file. If it's convenient for you, you can even pass it multiple config files. So we do that, for example, because we have kind of some default Cryosphere settings, and then we override those defaults with a few run-specific settings. So that's a common thing to do. So if you want help setting up a config file that's sort of for a campaign and then a config file that's for a run, we can help you with that process too. So you can run on the compute nodes. That's definitely preferable than running on the login nodes. I've gotten in trouble at NERSC for running on Cori login nodes, and I've gotten in trouble for running on login nodes on Cooley. So I think you should learn from my mistakes and always submit batch jobs for MPAS-Analysis and E3SM diags and the other diagnostics packages. So if you were to run on a laptop or on a compute node, in an interactive mode, you would see kind of a taskbar showing up, and it'll just tell you how far along the given analysis is with the given set of tasks and how much time is left. And eventually when it finishes, if it's been successful, it'll just say there's a log for each task. By the way, there are about 300 or 400 tasks, so that's a lot of log files, but they all end up in this one logs directory that you can browse through if that's important information for you. And then it'll tell you how long it took to set up and how long to run, and that it generated a web page, which is basically your indication that it was successful. So at the end of it, the idea is that you either copy and or change the permissions on the web page that results and put it in a web portal somewhere so you can show people your fancy diagnostics results. So the web interface starts out looking something like this. So there's a typical sort of main page, just a link for each of the two components, ocean and sea ice. And then at the bottom, we have some provenance that's helpful for kind of recreating that simulation if you needed to. So basically what command was run, which version of the analysis, if it's from GitHub, which hash, and then the config files that were produced. So that's all helpful for recreating it. And then there's an ocean page with a bunch of quick links to different types of analysis that I'll look at in a moment. And a corresponding sea ice page with more limited analysis, but still these quick links to the different types of analysis that we have. So I mentioned that there are some log files. Those can be useful if specific tasks are experiencing errors, because you'll have to look in those log files to find out what's gone wrong. So you might want to grep for the word error. So that's a standard. Basically, if Python throws an error of some sort, it's going to have error in the name, capital E, lowercase the rest. So yeah, you might take a look at that. Obviously, if you run into trouble and you're running into errors, you can also get in touch with us or create an issue on GitHub or that kind of thing, and we'll try to help you track it down. Okay, so that's getting started. Here are some example results to get you interested in maybe what MPAS-Analysis can do for you. So some of the most basic things that we can do are temperature and salinity maps. We do that at various depths. So at the sea surface, we can do it at, say, 200 meters depth, or we can do it at the sea floor. And we can also look at salinity. We can look at different regions, so the Arctic, the Antarctic. And so these global Arctic and Antarctic are the three regions we currently focus on, but it would not be difficult to add more regions. So if you end up with a region of particular interest, we can just figure out how to make a map for it and make that a new standard possible sort of projection for displaying simulation results. We do plots of mixed layer depth versus observational data sets. We look at the change in ocean heat content over the course of a simulation. We look at sea ice concentration and thickness as maps and compare them with observations where they're available. And then we look at time series of sea ice volume and sea ice area, and we can compare those against at least typical cycles. We don't have a good data set of sort of full time series of sea ice volume and area to compare against. So these are more canonical volumes, as I understand it, at least, kind of an annual typical cycle. We can look at the meridional overturning circulation. So obviously in this case, there might be observations of specific transects through this, but there aren't observations of the overall global meridional overturning circulation or the Atlantic meridional overturning circulation. But we can, for example, compare them between different E3SM runs to get a sense of whether it's getting stronger or weaker and where that might be happening and that kind of thing. And we also have a diagnostic. So this isn't a terribly good example of it, but we have a diagnostic of the El Niño index, and that can be used to kind of get a sense of whether the El Niño statistics are reasonable. So this is the time series. We also have a spectrum that you can look at instead. For simulations with sufficient resolution, we have the option to look at the Eddy kinetic energy. So this is actually a simulation that's maybe not quite high enough resolution for Eddy kinetic energy to be useful most places, but this is the proposed revision 2 of the water cycle mesh for E3SM V2, and it would have high enough resolution, at least in the Gulf Stream region, that it should have the kind of eddy dynamics that we're used to seeing. We can do temperature and salinity diagrams. So one axis is salinity, another is temperature, and this is a useful way to look in a sort of region. So in this case, we're looking in 2 different adjacent regions in Antarctica and trying to see basically in our simulation, do the different types of water properties kind of follow the curve that the observations and another set of model results suggest they might. So that can be very useful for figuring out, if a region's too fresh, too warm, that kind of thing, and maybe why. We have capabilities of looking at transects through the ocean, which is a vital part of understanding certain types of dynamics, like, for example, this sort of slope front that happens right at the continental shelf break around Antarctica. We can look at different properties, so looking at temperature, salinity, and potential density in this case. We can look at velocity and other properties as well. For the cryosphere, we're particularly interested in melt rates around Antarctica, and we do a set of simulations that includes the cavities under ice shelves, so we can simulate those melt rates directly. And so we can do maps and compare with satellite-derived sort of quasi-observations of melt rates, kind of see that we're in the right neighborhood at least, and then we can look at time series, and those can be over different kinds of regions, so all of Antarctica, sub-regions of Antarctica, or even specific ice shelves or basins within Antarctica. I mentioned that we do Arctic and Antarctic maps, and that's for a number of different fields, so just reiterating that, that we kind of explore those regions in particular in the cryosphere configuration. And then we also have support for a number of biogeochemical tracers. So looking at the surface of the ocean for now, at least, because that's where we have satellite observations to make good comparison. So I put up 3 examples here, but I believe there are 8 or 9 different fields at least that can be compared against observations. And so we have O2, PCO2, and CO2 gas fluxes as just some examples. Okay, so I'm going to go through a few configuration options, and I'm going to try to do this a little bit quickly, with the idea being that you can always go back and look at these slides, or you can go back and look at the tutorial. But I just wanted to make sure that at least the basic config options are kind of known to everybody, so you're not too surprised at where to get your hands dirty if you need to. Okay, so we have an example config file that's in the repo. There's a link here. You can find it pretty easily. And that's really the place to start. Or you can start with a config file that's specific to the machine you're working on if you're working on one of the standard E3SM supported machines. So we have a configs directory, and there's a bunch of examples there too. So one of those two is basically the starting place. So you have various what are called sections, with different options within each section, and I'll go through the most important ones just real quick here. I mentioned that we have a specific configuration file for polar regions, so the Cryosphere campaign, and then kind of another project that's also interested in high latitudes, the High-Lat project in COSIM at LANL. And this is a useful way of having kind of, say, a standard set of plots that's different from the defaults. If your specific configuration maybe needs the same changes to be made over and over again each time you run the analysis. So something to talk to us about maybe. And then you would also need a corresponding job file, a job script on most of our supported machines. So here's an example from Corey, and we have a bunch of other examples also of different job scripts that you could look at to help you get started. The gist, though, is that you're just running on a single node with a single processor, the MPAS-Analysis executable, and giving it a config file. And despite us running on one processor on one node, you're actually using the full node with task parallelism or with thread parallelism. Okay, so the most common configuration options that you're going to have to change are, for example, the name of the run that you're going to do. So that might be the name of an E3SM simulation, but you could also make it something shorter. It's going to show up in lots of titles of plots or captions or that kind of thing. So you would possibly want something a little bit pithier if it's, for example, going to go into a paper, something a bit longer if it's important for everybody in the project to know exactly which simulation it was. Then if you're, when you're running MPAS-Analysis, you need to be able to run it on with multiple threads. So basically multiple tasks at once. And to be able to do that, you just change this execution so that you run with something like 6 to 12 tasks rather than one. That'll speed things up a lot. It'll also use a lot more memory, so you have to kind of figure out what the magic balance is for the specific node you're running on. And that's again where the example config files will be helpful. And you probably want to run NC-Climo in background parallel mode as well. So that's something to probably change from serial. You need to point to a diagnostics directory, and that diagnostics directory is either something that you would manually download if it's for your laptop, or it's a standard location on all of the E3SM supported machines, where you just point to that and all the diagnostics are already downloaded there. And so you just have to look at the example config files to figure out where that is for your machine. Okay, so then obviously, you have to somehow point to the simulation you want to analyze, so that's the input section. And so the main thing you'd probably need is some base directory of some simulation. And then you might need to specify some of the subdirectories where maybe you've short-term archived some of the output or something like that. Please ask if you need help with that. Same with the nameless and streams files that I mentioned before. You might need to point to those. And then the last thing, and it's actually pretty important, is that you need to give the MPAS mesh name, and it needs to be the correct one, for especially if we've pre-computed mapping files and things like that. You'll save yourself a lot of time by getting this name correct so that it can find the correct pre-created mapping files for a given mesh. So right now that might not be critical because we're still playing around with a lot of the V2 meshes. But as soon as we have those V2 meshes finalized, we'll give them a standard name, and this name needs to correspond to that. So ask me if you have further questions about that. The output is pretty similar to the input. You just give it some directory where you'd like to put all of the analysis that you've done. So it's really a matter of taste how you want to organize that. So we often do the simulation name and then the number of years over which the climatology is being run, but you can really do whatever makes sense to you. And you can have a separate directory for HTML output. The default is that it's just an HTML subdirectory within the base, but it's often useful to have it dumped directly to the web portal. So all you have to do is change the permissions. You can pick what analysis you want to generate, and that's a pretty complicated process that I'm not going to be able to get into in this discussion, but it is very important. It might not be useful to try to just generate all of the analysis. It might be useful to figure out which ones you want to skip. And so I or somebody else familiar with MPAS-Analysis can help you through that process of basically figuring out what's going to work and what isn't really useful for a given set of analysis. And lastly, you would want to set the range over which you want to compute climatologies and the range over which you want to compute time series and indices. You can set the end year to be end in any of these cases and just run through the end of the simulation. And it'll figure out what the last available year is in that case. So for time series especially, that's frequently something that you want is just give me the longest possible time series. Okay, it looks like I don't have a ton of time, so I'm going to go pretty quick through this under the hood stuff, maybe skip a little bit of it to make sure there's a little time for questions. So we compute climatologies automatically in MPAS-Analysis. There's no way at the moment, and certainly no need, to try to compute climatologies ahead of time. And I just mentioned that because I know that that's different from E3SM diags, where computing the climatologies in advance is part of the workflow. We do require these observations that I mentioned before that either have to be on one of the supported machines or you have to download using a script. And I just wanted to mention that those are on the sort of E3SM web server. So you could also browse through them if you have some interest. So these are the observations that are publicly available for the ocean and sea ice. Some of the basic mapping files, and we'll be filling those out with the V2 mapping files soon. Some what we call region masks, so basically some definitions of how to break the ocean into regions for various types of analysis calculations, averages or that kind of thing. Typically it's spatially averaging. We also have a few private observations where we don't have permission to make them public, and so we keep them internal to the project on Anvil at this location that I'm giving there. And I always sync them across all of the supported machines. So if you want to add new private observations, you would put them in here and ask me to sync them across all of the supported machines. Okay, and then basically we have a few supported meshes now where we have mapping files already created. And there's going to be a lot more to come. I'm not going to go into those in any detail because I don't think the supported ones are terribly important for most of you. But one thing you should know is that it's possible to start with a new mesh, and MPAS-Analysis should mostly work right out of the box with a new mesh without you having to do anything. You can just give it a name that it's never heard of as the mesh name, and it'll generate the mapping files and everything that's needed. But it's often slow and memory intensive. So if you run into problems, you should get help caching basically the mapping files and region masks. And I'll have a tutorial set up sometime pretty soon for that. So that's a separate tutorial from the one I mentioned earlier. Okay, so 3 future plans. One is something I've been working on for a couple of months. It's nearly done. And that is we want these transects that I showed you before to actually be on the native MPAS mesh and to show a lot more detail of basically how the MPAS mesh actually looks. So you can see these jagged features under ice shelves. We actually want the transects to show that that's how the model sees these the bathymetry under ice shelves, for example. Something we want to improve in the future, and that's part of the reason I don't want the transects to hide the sort of warts and all features of the model at the moment. One of the other things we'd like to do is add some really nice analysis that one of our postdocs who just actually is heading back to South Korea. So this is Hyein Jong, and she did a lot of work on water mass transformation and also on sea ice fluxes. And I think both of those would be really great additions to MPAS-Analysis that we've been wanting to do for quite a while. And then finally, one of the problems we're running into is we're running hundreds of different tasks in parallel, but that's really more than one node is capable of handling, both in terms of memory and just in terms of sheer number of tasks. So analysis takes several hours on typical runs at this point. We really need to be able to support node parallelism, and the way I'd like to be able to do that is with this software called Parcel. So that's something I will look into in the future. And that is it. Thanks very much.